Okay, good afternoon, dear abstract algebra students. Let me now provide you with a supplemental instructional video. I feel there is a need for this because although you are assigned to read on something, some concepts that you already know, because those are just about set theory and the early concepts of algebra. But then I feel that there's really a need to highlight some of the concepts to help you understand the concepts of abstract algebra better. Okay? So the first pages of our book talks about sets and relations. I know you already are familiar with this. So we have here the definition of a set as a well-defined collection of objects or ideas. Okay, and then those elements or the things that are in the set are what we call the elements of the set. The symbol is this one. So if there is an element which is not, or there is an object, let's say B, which cannot be found in S, so we say that B is not an element of S. Okay, so this is our symbol for not an element. Then next we have the notion of the empty set. This is the set with no elements. Okay, the set with no elements. This is our symbol for the empty set. Next we have the definition of what is well-defined. When we say well-defined, we clearly know what elements are in the set and what elements are not in the set. If it is not certain whether this element is in the set or not in the set, then the S is just a collection but not a set. Okay? A set is always well-defined. So that distinguishes a set from a mere collection. Next, we are reminded that every definition is an if and only if statement. Even if it is stated in a conditional form, we must always remember that it is always a biconditional statement when it is a definition, considered as a definition. Okay, next we have here the definition of a subset. This would be our basis if we are asked to prove whether or not a set is a subset of another. So we define a set B. A set B is a subset of a set A, denoted by this symbol here. Okay, this one here. Or A is a superset of B if every element of B is in A. Meaning, if a thing can be found in B, it should be found also in A. Okay? Next, this symbol here is our symbol for B being a subset of A, but B is not equal to A. Okay? This symbol here. If we are not sure whether there are elements in A which cannot be found in B, we make use of this symbol. Okay? So we only use this symbol if we know that B is a subset of A, but A is not a subset of B. By the way, when we say A is not a subset of B, meaning there are elements in A which cannot be found in B. Okay? So that is how we prove that A is not a subset of B. So by this definition, if we are asked to prove whether or not B is a subset of A, we just have to show that if an arbitrary element X is in B, it should follow that this same element X should also be in A. Now, since X is arbitrary, means it represents any element in B, therefore we say that all elements in B can be found in A. So it should follow that B is a subset of A. Next, we have here the definition of the improper subset. If A is any set, we say that then A is the improper subset of A. So in other words, any set is a subset of itself. It is a special subset called the improper subset. Okay? Then any other subsets of A, if there are other subsets, they are called proper subsets of A. Okay? Next. So we can see here examples. So if S contains the elements 1, 2, and 3, then if we are to enumerate the subsets of S, it would be first the empty set, then the singleton set containing 1, singleton set containing 2, singleton set containing 3, and so on until the set S itself. So if we would count them, there would be 8 subsets of S containing 3 elements. Next, we have here the definition of the cross product or the Cartesian product of A and B. So the Cartesian product of two sets A and B, denoted by this symbol A cross B, will be the set of ordered pairs. Okay, ordered pairs, wherein the first component are elements in A and the second component are elements in B. Okay, so all ordered pairs of this form would be elements of the cross product of A and B. For example, suppose we have a set A with elements say 1 and 2, and then B has elements, let's say 3, X, and Y. So if we are to take the cross product or the Cartesian product A cross B, this would be the following ordered pairs. First, we have 1, then 3. Next, we have 1, then X, then 1, Y, then we have 2, 3, let's move first here, next we have 2, X, and 2, Y. Okay, so these are the only ordered pairs that can be formed if the first components are found in A and the second components are found in Y. So all in all, there would be 6 elements in the cross product. Okay? So we'll just go back at that example later. Next. Here's another example. You can just go over this yourselves. And then we have here the notations used in this book, or the symbols. This symbol here, is what we use to symbolize the set of all integers, meaning those are whole numbers, positive, and the negative of those whole numbers, then 0. Q, this symbol is the symbol for the set of rational numbers, which are numbers that can be expressed as ratio expressions or quotient expressions, meaning these are expressions of the form m over n, where m and n are both integers, and n, the denominator, should not be 0. Otherwise, it is not a rational number. It is not even a real number. Okay? Next, we have the symbol R for the set of real numbers. Here, we have superscripts plus to indicate positive subsets, or the subsets of this with only positive elements, meaning this is the set of positive integers, this is the set of positive rational numbers, and this is the set of positive real numbers. This symbol C is used to represent the set of complex numbers. Okay, then we have here the superscript asterisk. The superscript asterisk in each of these set indicate that these are subsets of integers, rational numbers, real numbers, complex numbers respectively, but do not contain 0. So this symbolize non-zero integers. This one symbolize non-zero rational numbers, and this one symbolize non-zero real numbers. This one symbolize non-zero complex numbers. Okay, then we have a particular cross product or Cartesian product. I know you are familiar with the Euclidean plane or the Cartesian plane. Actually, the Cartesian plane is just the Cartesian product of R and itself. Okay? So that is the Euclidean plane, diba? If we are to take the cross product R cross R, it would be the ordered pairs. This would be ordered pairs. This one would be ordered pairs A, B, wherein A is a real number and B is also a real number. So all ordered pairs of real numbers would be elements of the cross product R cross R. That is why the Euclidean plane or the number plane, or we call this the Euclidean plane, because these ordered pairs can be represented as points on the plane. So the Cartesian plane is just the graphical representation of the cross product of R and R. That is why sometimes we symbolize that by R squared. Okay. Next, we have the notion of relations. Okay. A relation actually mapping or pairing two sets, let's say set A and set B, is just a subset of the cross product of the sets A and B. Okay? It is a subset of the cross product. Then if that element, this ordered pair is an element of the relation, so when we say AB is an element of R, is also the same as saying A is related to B. Okay, let us go back to our example, earlier example. Okay, so we see here that the cross product A cross B has the elements 1, 3, 1x, 1y, 2, 3, 2x, y. So suppose we define a relation R. Okay, but as I've said, a relation is a subset of the cross product. So let's say we'll just have to take some, not necessarily all elements of the cross product. So let's say we take 1, 3. We also take, let's say, 1y. And let us just say 2, 3. Okay? 2, 3. So suppose these three are the only elements of the relation R. Okay? Take note that R here, by the way, we say that R, since R is pairing A and B, so we say R maps set A to set B. Okay? So what is meant by this symbol is that R is a relation taking elements of A to pair it with elements in B. Okay? Tando na lamang mo. Punta madali. Sige. So again, we have R. R here is a relation containing elements 1, 3, 1y, and 2, 3. So, here, since 1, 3 is in R, we could also say that 1 is related to 3. Since 1, 3 is an element of R. Also, 1y is in R, so we also say that 1 is related to y. And also 2 is in R, meaning 2 is related to 3. Okay? Note that there are elements in the cross product which we have not included in R. For example, 1x. Since 1x is not in this set of ordered pairs, so 1, therefore, 1 is not related to x. Okay? In the same manner, 2 is not related to x. 2 is not related to y because these elements are not in R as what we have defined R to be. Okay? I hope that is understood. Okay, so again, a relation between sets in A and B is a subset R of A cross B. We read the ordered pair AB is an element of R as A is related to B. Then we write A, R, B. So we read this as A is related to B. Okay, a very familiar relation is the equality relation. Equality relation. Diba? We say that let's say 1 equals 1, 2 equals 2. Okay? So, in other words, the notion for equality is that we're referring to the same element. Okay? They are just one and the same. That is why they are equal. So, we define therefore the equality relation as equality, or this relation is the subset of ordered pairs x, x, wherein x is an element of the set S of the cross product x, S cross S. Okay? Therefore, for any x in S, we have x is equal to x. But if if x and y are both in S, but they are different elements of S, so we say that xy, the ordered pair xy is not an element of the equality. So we write x is not equal to y. Okay. Then recall that ordered pairs can be thought of as points on the Cartesian plane. Okay? If we would plot all of those points, we would be able to form a curve. Such curve is what we call the graph of the relation. Okay? Now, some relations are special such that they are called functions. So if you would recall what a function is, it is a relation pairing each element in the domain a unique element in the co-domain. Meaning, no element in the domain is left behind, and it should be paired with exactly one element in the co-domain. Meaning, no element in the co-domain would share the same element in the domain. Okay? So, for example, here we have the function f defined by the equation f of x equals x cubed. Meaning x from, again, this is a real valued function. Meaning f maps the set of real numbers to itself. So x here, x in R, is being paired by x cubed. And since R is a real number, x times x times x, which would also be a real number, meaning x cubed can also be found in R. So in this definition of the function, f pairs x with x cubed. Okay? Meaning an element of this function can be 1, 1. Because the cube of 1 is 1. Another element of that function is 2, 8. Because 2 cube is 8. Or let's say 1/2 would be paired with 1/8. Okay? Notice that all first components are in R, are elements in R, or they are all real numbers, and the second components 1, 8, and 1/8. 1, 8, and 1/8 is also in R, only that they are cube of the first component. Now, as I've said earlier, if we are to collect all of these elements, all possible elements, then plot it on the Cartesian plane, we would be able to form a graph or a curve. So it should look like this, for example. It should look like this. let's say this would be the positive part of the graph, there would be a negative part of the graph. Okay, so this curve consists of all points wherein y, or the value of y, is just taken from the cube of the value of x. Okay. Next, we have the definition of a function. A function phi, mapping or pairing x into y, is a relation between x and y with the property that each element x in x appears as the first member of exactly one ordered pair xy in the function phi. Such a function is also called a map or a mapping of x into y. So this is the symbol for the mapping. So x is what we call the domain, and y is called the codomain. Okay, the range would be the set of all elements in the codomain which were taken as elements of the function. Okay, so we say that the range of phi is phi of x. Okay, the image of x. This would contain all phi of x such that x is in the domain. Next, we have the notion of cardinality. Cardinality is just another term, term for saying the number of elements in the set. Okay, so if two sets have the same number of elements, they would have the same cardinality. Okay, let me first stop right there. We shall continue with the discussion of this in our next video. Thank you for watching.